I want to talk about sound waves, but the lecture I'm going to give you on sound waves is going to answer some of the conceptual things that I think will help you on the quiz. So let me go ahead and get this going for you. So sound waves, you guys read, or hopefully you should have read at least, the fact that the sound wave is 340. This is more exact. It's actually 343. But in your textbook, I think it tells you it's 340 meters per second. To give you some context, that is 1 mile in 4.7 seconds. Really fast, right? It's actually not fast, so fast that we can't perceive it. So I'm going to show you some videos where you can actually see how delayed sound is if you're really standing far apart. Question?
Not like when you see the flash of lightning, figure out how far it is.
Perfect. Exactly. So that whole theory of waiting for the thunder to crash after you see a lightning bolt, that lets you know how far the lightning actually is, because the longer it takes for that crash to sound in your ear is the delay of that sound wave, because light travels a lot faster than sound. So I'm going to just play this video because who doesn't like Homer Simpson?
Majestic eagle, just like me, unashamed of
Oh, sorry.
his baldness.
Did not mean to do that.
Oh, beautiful. He probably sees a mouse he wants to tear in half. Oh! You've been totally building his brain
since he was on a vocabulary test you aced. But after some thought, all my worries went away. I know the answer. I'm going to force you to turn yourself in. Good luck with that. The only thing that'll change my mind is a sign from God. Oh!
Son, it was so beautiful. I went faster than the speed of sound.
Well, Bart, is that enough of a sign for you? All right, I'll turn myself in. It'll give me a chance to work some more on the detention quilt.
So this is obviously a joke, but you can actually move faster than the speed of sound, and I'll talk about that a little bit later. Here's another video. So this is a video of Mr. Burns, who used to be a physics teacher here. I know, right? I didn't even see that connection. Mr. Burns used to work here at this school as a physics teacher, and I was really excited to work with him because I had been taking his workshops when I first started teaching physics, and turns out I was replacing him. So we no longer have Mr. Burns, but his video of this speed of sound demo is really good. I want you to pay attention to when you see him hit that drum and when you hear it. So notice how he stops and you still hear that last beat after he stopped drumming. So this is a camera that's obviously zoomed in really far, which is why Mr. Burns is so blurry, but they were standing all the way at the end of the track in the football field. And so the delay of sound, like I said, is actually, you can perceive it if you are far enough. Okay, here is the Doppler effect. You read about the Doppler effect. How many of you are Big Bang Theory fans, watch it often? Oh man, this is the first class where I didn't have a handful of students lift their hands. Okay, I know some of you do. You're just in hiding.
Oh, it's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay. See, people get it.
Hi.
Hi, hello.
Now, what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
The Ray Davis choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
If that is some sort of learning disability, it's very insensitive.
Why don't you just tell people you're a zebra? Why don't you just tell people you're one of the 7 dwarves? Because I'm a grown-up. Yes, well, I'm the Doppler effect.
All right, so he gave a really good, concise definition of the Doppler effect there. But here's basically what he said in his, Sheldon speech. If you are standing in front of an object that's moving, your source is the object that is creating the sound. Most of the time, your source is standing still, and everything is moving at 340 meters per second. As the car approaches the observer, the frequency of that sound, these sound waves get closer and closer together. And if you decrease the frequency, you increase the wavelength, and you increase the pitch. You increase the frequency and you decrease the wavelength. So here we've got a really high-pitched sound anytime your source is approaching. Once it passes you, you get a low pitch, because now these wavelengths are further apart. And the lower your frequency, the lower your pitch. So the effect, this is an overview of what it looks like when your sound waves are emitting outward from the top view. I want you to notice just one important thing, that as the source approaches, you get short wavelengths and you've got long wavelengths. Because sound emits at 340 meters per second, but now you've got this added motion of your car or your object moving at a fast pace added onto it. So it makes those sound waves move faster. So these are your sound waves. This was exactly what Sheldon was talking about. The sound of a train gives a perfect demonstration of the Doppler effect, as well as ambulances and like police cars that have their horns on as they're driving by. So you can hear that change in pitch, right? It starts high and then it goes low. If you didn't hear it well enough, I'm going to do a demo. And I almost knocked a student out with this demo because I didn't tape my battery in hard enough. So I'm going to try to do better this time and not get myself in trouble. Okay, so you're going to hear that pitch, and it is pretty constant because I'm not moving, or the source is not moving. Once it starts moving, though, you hear the change in pitch? Pretty cool. So now you've got sound waves approaching you and moving away from you. That is your Doppler effect. Okay, I'm going to stop torturing you now. Okay, so there, just like the Homer Simpson video, there is a scenario where you can move faster than the speed of sound, and we call it sonic boom. And I think I remember a student doing a little concept on this when we did the fall project. Was it Yusin? Yeah. So the sonic boom is a scenario where you've got your object moving faster than the speed of sound, and then you get something called a shock wave, and it causes the sonic boom to take this cone shape. this cone shape then trails behind the object so that once that object has already passed you, you hear the sonic boom in kind of that delayed time. And I'm going to show you a video of this. So this person isn't going to hear anything. Even after it's passed, it may not hear anything. And this is the cone shape that happens. You can't see it in the video, but if you look up sonic boom, you're going to get a lot of images with kind of like a cloud of smoke in this cone shape. So the sonic boom, like I said, is delayed. A person, even after the plane is passed, a person here won't hear it until this cone actually approaches them. And I want you to pay attention to the video. And if you look at it, you can't even see the plane anymore by the time the sonic boom happens. So let's watch this. Okay, so the plane is passed. You can't see the plane. It's gone. And there's your sonic boom. So it's pretty delayed. And it's really cool once you eventually hear it, how the plane is no longer in sight. So the last thing I wanted to show you is one demo, really. So this demo, where is it? I call it my music box guts because I don't actually have the box part of my music box. And if I were to turn it, can you hear it? A little bit. Can you hear it, Andrew? And then how about Thomas in the back? Can you hear it? Very slightly. Okay. Now I'm going to give my music box a box. I'm just putting it on the table, or for those of you who can't see it on the table, it's like it's on speakers when it's in the music box, right? It's significantly louder. So here's something about sound waves that you want to know. It kind of goes against our previous understanding about waves in general. The more dense your medium, the faster your sound wave travels. What did we say about the density in terms of slinky waves or any other waves? What did we say the density had to be in order to get the speed faster? Adele? It has to have lower density. Sound waves are different. Sound waves are the opposite. It has to have high density to go at a faster speed. So in air, 340 meters per second. In water, even faster. On a solid surface like a music box or a table or a whiteboard, it goes even faster. So, question. I've never actually heard of that, but it's the same type of theory. I mean, have you ever heard of like putting two hands on a string? Right? If you haven't done it as a kid, you've seen movies where kids do it and they talk to each other from the treehouse to their bedroom or to neighbors. That string is the medium in which your sound wave travels. And because it's a dense medium, more dense than air, you can hear your friend from a further distance. So, unlike sound waves, your test isn't going to be on normal waves. So things that affect the speed for normal waves is not high density, but low density. You want low dense objects if you want your speed to travel faster. Because like your Slinky, if your plastic Slinky has less density, it has less mass to move, so it can move faster. What are the other things that'll affect the speed of a regular wave? Rena. High tension. If you think about guitar strings, if you tighten them, you're going to get a higher pitch. High tension means it's going to move faster, greater wave speed. And what's the last thing? There was one more. I like it. The type of wave. So which type? We only have two types. Which type moves faster? The longitudinal. Because you've got the parallel displacement. They're going in the same direction. The particles in the medium and the wave speed itself are in the same direction. And in a transverse wave, you have to move in perpendicular direction to the wave speed, and it just has more displacement that way. It takes longer to do that type of displacement. So those are the last few concepts that you want to know for this lab, or sorry, for this quiz that you're taking. Any questions? Okay, we're going to take the quiz next, and after you take your quiz, you're going to work on this worksheet. There's a change that I'm going to need to make for this lab. Under one open end, I want you to change, instead of 1, 3, 5, 7, just change it to second, third, and fourth. And then the number of waves, this N section means the nth harmonic. Each of these are a harmonic. Now, in a one open end instrument, you actually do go by one, first, third, fifth, and seventh, but it's hard to find a pattern like that, so I'm going to change it. And then in the simulation, I want you to try to find a pattern between the harmonic number and the number of notes. The harmonic number and the number of antinodes, and the harmonic number and the number of waves. You're going to see that there's a consistent pattern, and you're going to give me an equation. This one is too hard of an equation to figure out, so I'm going to give that to you later, but just do the first two for this last one, and then the other charts, you should be able to fill this out. So I do want to see all the patterns that you notice for the rest of the equation. And then again, bottom, instruments, leave that for the last 10 minutes of class. So I want to talk about the pattern. When we had the two fixed ends, my n harmonic means any harmonic. What was the pattern from the harmonic number value to the node number value in the two fixed ends one? Sam?
The number of waves is n plus 1.
It always increased by 1, right? How did it change for the antinodes? Did the harmonic and the antinode have a pattern? Zoe? It was the exact same. Now the wavelength, or sorry, the number of waves is a little bit harder, but who found a pattern between the number harmonic and the wavelength? Alec? N divided by 2, or n times 1/2. What about one open end? If I had one open end, what was the number of nodes and the number of antinodes? Because they should have been the same. How did that compare to your harmonic? What was the pattern for that one? Should have been pretty easy to see. Let me have someone new. What was my pattern? All right, Alec, what was it? It was the same. Your node and antinode should have been the same number as your harmonic. The number of waves is a little bit harder to find a pattern for, so I'll give you that equation later. And then last one, two open ends. What was my pattern for that one? My node pattern, Sam.
The node pattern is the same.
The node pattern was the same. And then my antinode? Any thoughts? Someone new besides Sam and Alec? Sucko. N plus 1. Good. So it was the opposite. 2 open ends and 2 fixed ends. 2 fixed ends is the same as 0 open ends. Is flipped. It means the number of nodes and the number of antinodes are going to switch. Now, when you look at your musical instruments, you've got these harmonics relate to a harmony, like you think of when you think of music. And when you play musical instruments, you've got 2 types. You've got string instruments and you've got wind instruments. String instruments always have 2 fixed ends, kind of like a guitar where you've got strings connecting, or a cello or violin. You've always got both ends of your instrument are fixed. That's the same as 0 open ends. So, when I'm talking about the instruments, which of these instruments would be my 0 open end? The guitar, obviously. Now, there are instruments where you only have 1 open end. When I was in high school and middle school, I played the Josh. Like, where's the memorial, man? Focus. Okay. You too. Okay, so when I have 1 open end, you can have instruments like the flute. I used to play the flute when I was a kid. You blow into one end and it comes out the other. The other end is closed or it's fixed. You can have instruments like, for example, blowing into the top of a bottle. You can make a tone out of that. One end is closed, one end is open. And then they have an instrument here that doesn't necessarily involve a tube or blowing into some tube with an open end. But can anyone think of which one has 1 open end in these musical instruments? Sam? The thumb piano. Because you flick one end, it's free to move, but the other end is fixed. And then last but not least, panpipes are 2 open end. I have a 2 open end instrument. Actually, it's not an instrument. It's called a whirly tube. But I can create harmonics, and it has 2 open ends. This is the first harmonic. This is the second harmonic. This is the third. And the fourth. Okay, I'm winded. But I should have done it music. Or whirly tube performing. That was my other calling. But you can make sound out of tubes with 2 open ends, 1 open end, and the string instruments would be 0 open ends. All right? Okay, so your homework. Finish homework 6. Finish this worksheet if you didn't. Answers are going to be online. Homework 6.6 is a concept builder and extra credit. Take advantage of it. It is there for you. You are welcome.
Thank you.